Welcome to PM Ready, your guide to becoming PMP certified. This is the lesson on Quality Tools, Part 4. Now we come to stratification, which is when you have multiple histograms merged into one. You didn't think you had multiples when you started, but when you graphed the data using a histogram, it showed multiple peaks or a comb, or something that made you suspect that you have two or more data sets that you thought were the same, but are somehow different. Or the distribution may not lead you to suspect multiple data sets, but they're there anyway. Take our example of web page load times that showed a skewed distribution. For time measurements like this, a skewed distribution is just what you'd expect to see. However, you might wonder why it sometimes takes so much longer to load the page. To stratify the data, you need to get creative and figure out different ways to divide the data into logical groups. For our load time data, you might notice that the measurements were taken at two different locations. So, separate these data into these two groups and create a histogram for each location. In this case, you can see that your skewed distribution is actually a combination of two normal distributions. Load times are longer and more spread out at location A, while they're shorter and tighter at location B. Now you can ask yourself, what's different between location B and location A that makes location B so much faster? And can we use that information to make location A faster? In addition to dividing the data by location, you could divide it by time of day, day of the week, or day of the month. You might find that response times are better in the mornings, or better earlier in the week, or terrible when accounting is doing month-end processing. Or it could depend on the browser, or on the person running the tests. Until you try dividing up the data in various ways, you won't know. Stratifying the data can point you in the right direction for where to look for root causes, which can lead to all sorts of quality improvements. Here's an example of a scatter plot diagram. It compares two variables and shows the relationship between them. For example, the horizontal axis could be time spent studying for an important exam, and the vertical axis could be the score on the exam. Each dot would represent an individual, how much time they spent, and what score they got. In this example, it shows that the more time people spent studying, the better score they got on the exam. You can see that there's a strong relationship between study time and exam score. How much you study seems to be an excellent predictor of how well you'll do on the exam. This relationship is sometimes summarized or highlighted by drawing a trend line that shows the average relationship between these two variables. In this case, you'll notice that there is one point that's an outlier. Someone scored really well without studying much at all. When you have a few exceptions like this that don't follow the trend of the rest, these exceptions are called outliers. There's usually an explanation for outliers. Perhaps this person misunderstood the question, and when everyone else responded with how many hours they spent studying, this person reported their study time in days instead of hours. Or it could just be a typo. Looking at the rest of the points on this scatter plot diagram, when two variables are related like this, it's called a correlation. Correlation analysis is a more formal way of proving a relationship between two variables, but a scatter plot diagram is an excellent way of visualizing this relationship. The trouble is, just because two variables are related doesn't necessarily prove that one causes the other. That requires more work, which is beyond the scope of this discussion. However, you should know that when you find that two variables have a correlation, there are three possibilities. The first variable could be causing the second, or the second could be causing the first, or there could be a third variable that's causing them both. In this case, it doesn't make sense that scoring higher on the exam causes more study time because these variables happen in a certain order: study, then exam. It could be that more study time causes higher exam scores. Or it could be that there's another factor not shown here that's causing both more study time and higher exam scores. Maybe it's IQ, or maybe it's the course they took, or time spent with a tutor. Maybe the outlier did so well because they spent more time with a tutor than anyone else. Maybe tutoring time is the better predictor of exam scores, and study time usually but not always correlates as well. In statistical terms, when two variables are related, it's called a correlation. And when you can show that one actually causes the other, then it's called an association. The process of determining if and how variables relate to one another is called regression analysis, which can include scatter plot diagrams as well as other tools. Here are some examples of scatter plot diagrams with different patterns of relationships. The one labeled none is what you'd expect to see when two variables are not correlated. They aren't related. They don't appear to affect each other. They're independent. The one labeled weak indicates some degree of relationship. They do appear to be related, but the relationship's not particularly strong, but it's there. The one labeled strong positive, on the other hand, shows a strong relationship between these two variables. There's a high correlation between them. It's called a positive relationship because more of one is related to more of the other. For example, more time spent practicing the piano is related to higher levels of piano playing ability. Or more time spent designing quality in up front is related to higher quality outputs. Or the longer you wait to make a change, the more it costs to make the change. The scatter plot diagram labeled strong negative also indicates a strong relationship between two variables, but in a negative direction. For example, altitude and air pressure. The higher the altitude, the lower the air pressure. So far, these examples have shown linear or straight line relationships, but you can have other shapes of relationships, such as a strong exponential relationship, or even relationships that change directions, such as going up for a while and then going down. We covered stratification briefly using histograms, but they're generally easier to do with scatter plot diagrams, because you don't have to worry about bin sizes and you can see the individual data points all on one graph. This scatter plot for a software development project shows the relationship between the size of each code object and the number of errors found in that object. The results are separated into two groups: code objects that are part of component A, shown as blue circles, and those that are part of component B, shown as red triangles. You can see that component B is much more error-prone than component A. You can identify such patterns in the data by considering the different sources of the data and the different conditions under which the data is gathered. Whenever you see any interesting divisions like this, you can stratify the data to analyze the differences. Take a look at these scatter plot diagrams. The one on the left looks like it might have a weak negative correlation. Based on this, you might decide to design some quality controls around this negative correlation. The one on the right doesn't seem to have much correlation at all, so you might conclude that any attempts to influence these variables would not have any impact. But let's take a look at these exact same diagrams with some stratification. Keep in mind that these points have not moved. All that's changed is that they've been stratified by dividing them into different logical groups. The first one on the left shows that there's not really a negative correlation. In fact, there doesn't appear to be much of correlation at all. But you can see that there's a tight grouping and a clear difference between these groups. Now you know that you need to look into why the data is different between these groups and see if you can use this to your advantage to improve the situation. The second diagram on the right, which didn't appear to have any correlation, now appears to have some pretty strong correlation going on. A positive correlation for one group and a negative correlation for the other. This is definitely worth investigating. Now we move on to another quality tool known as the control chart. These charts are used in statistical process control. On a control chart, each dot is a measurement. The range of measurements is shown on the vertical axis. Here, the range is 0 to 2000, with 1000 being the center line. On the horizontal axis, you have time. Each measurement is plotted on the chart, one after the other, moving from left to right. In other words, these measurements are shown in chronological order. Like with a trend chart, it shows how these measurements are changing over time. This chart is based on our previous example of the time it takes to load a particular web page, measured in milliseconds. Loading the page the first time took 1,000 milliseconds. The second time, it took 1,500 milliseconds. Then 400 milliseconds, and so on. A line is used to connect these measurements in chronological order. The dashed red lines are the upper control limit and the lower control limit. These are calculated based on the data, using some statistics that are a bit beyond the scope of this course. The key to remember is that they're not set arbitrarily, but calculated based on the actual data. If all of your measurements are within the upper and lower control limits, then your process is considered to be a stable process and is said to be under statistical control. On the other hand, if you have measurements outside of the control limits, your process is unstable. A certain amount of variation in the measurements is expected and acceptable for a stable process, but when that variation exceeds the control limits, something's going on to create more than an acceptable amount of variation, some sort of special cause. You need to look for what unusual factors are causing this. If you have several points in a row, all trending in the same direction, and extending outside of one of the control limits, then you have what's known as an unstable trend. Different people will have different rules of thumb for how many points it takes to make a trend. Some may say 4 or 5, while others say 7 or more. It's often easier to see it than to describe it. As you can see from this example, it looks like we have an unstable trend going on, and it looks like something suddenly changed to introduce it at about halfway through these measurements. You can also have what's known as a skewed trend. This is when all of the measurements are within the upper and lower control limits, which would indicate a stable process, but several measurements in a row are all on one side of the center line. In this case, you can see that about halfway through, a skewed trend emerges. Although you're still within the control limits of being a stable process, something's going on that needs investigating. The green lines on this control chart are the specification limits. These are the limits of acceptable variation of quality. These limits are set by quality standards, or end users, or customers, or your project sponsor, or even perhaps by the project manager. They mark the range of what's considered acceptable for the project or the operation. It meets the quality requirements. Ideally, your upper and lower control limits, which indicate what your process is naturally doing, are within your specification limits, which means that you have a process that meets requirements. On the other hand, you could have specification limits that are within or more restrictive than your control limits. We saw this with the truncated histogram, showing that some of the outputs of certain processes are unacceptable and need to be reworked or discarded. Your options are to improve your process to tighten up the control limits, or renegotiate the specifications, or live with having to rework or discard some of your outputs. Here's an example of a control chart that shows all of the lines. The upper and lower control limits are your red dashed lines, and these indicate the natural amount of variation of a stable process, and this is calculated statistically from the actual data. The green lines are the specification limits, which could be inside or outside your red lines. Hopefully they're outside, because these green lines indicate the range of acceptable variation for your quality requirements. A control chart is used to determine whether or not your process is stable or under statistical control. It helps you to detect the differences between normal variations and special causes of variations. Points that are outside of your control limits indicate to you that you have an unstable process, and you should analyze further to see if you can determine and remove any possible special causes that are causing these outlying measurements. Your control chart measurements come from your quality control measurements as part of your project's control quality process. Although you don't need to be a statistician to be a good project manager, you should have a solid understanding of a few basics. When you have a distribution, such as this normal distribution, sigma is a measurement of how far away a measurement is from the center line at the peak of the distribution curve. 1 sigma is the distance on either side of the center line that includes 68% of the measurements. 2 sigma includes 95% of the measurements, and 3 sigma includes 99.7% of the measurements. These percentages hold true no matter what, whether the distribution curve is tall and skinny, or short and wide, or anything in between. 1 sigma is still 68% of the measurements. If the curve is short and wide, 1 sigma is larger in that it extends farther away from the center line, but it still includes 68% of the measurements. This is known as the 68, 95, 99.7 rule, and you should memorize this. The Six Sigma quality movement is based on this concept of sigma. The goal with Six Sigma is to have your outputs meet quality requirements 99.99966% of the time. That's 5 nines, or 3.4 defects per million opportunities. For example, if your supplier of ball bearings says that 6 sigma is their goal, That means that out of every 1 million ball bearings they manufacture, they want their processes to be so good that no more than 3 ball bearings in a million are outside the specification limits. For those of you who are more statistically inclined, 3.4 defects per million is not actually 6 sigma. It's 4.5 sigma with a 1.5 sigma shift. And there are some good reasons for this adjustment, but they're a bit beyond the scope of this course. If you're interested, you can read more about it online. This lesson has covered a whole host of quality tools, from checklists through logical data models, stratification, control charts, histograms, one of my favorites, and Six Sigma. The objectives of this lesson are twofold. That given an example of a quality tool, you should now be able to, or at least once you've reviewed and learned all the material in these lessons, you should be able to identify the quality tool, state its purpose and its usefulness, and interpret the results that are shown in the quality tool. And, given a certain circumstance or need, you should be able to select which would be the best tool to use. The material for this lesson comes a little bit from the PMBOK guide, but mostly from other sources, many of which you can consult online. PM Ready is a publication of PM Guaranteed and is based on the Project Management Institute's PMBOK guide.